Suppose there are five people standing in a row. In how many different ways can we arrange these people? The obvious answer is 5 factorial, that is 120, which we have all learned in high school math. But what if I ask you, how many ways to arrange one and a half people? This seems weird at first glance, but why to bother about such question at the very first place? What's the motivation behind this? If we are anyway going to investigate this scene, we would essentially be talking about fractional factorials, probably negative and complex as well. The main reason is interpolation. For instance, a to the power m simply means multiplying a by itself m times. But this breaks when we talk about non-integer like half. The other reason is generalization. Suppose you want to find sum of natural numbers up to n. One way is to manually keep adding. The other hack is to just derive a formula and plug in n. This method saves a lot of time in computing. So why not do the same for factorials? Instead of manually computing 100 factorial, it would be really easy to use a formula for it. So our task is to find a formula for factorial. This could be done in several ways. The very first thought is to interpolate graphically. Go on, just grab a pencil and plot some points and try to draw a smooth continuous line passing through them. But the only problem here is that we end up realizing there are infinite ways to draw a curve like this, and thus we can't really be sure which one is the right one. The other one is expressing factorial as infinite series of product. This is very familiar to factorials itself. Around 1729, Euler himself tried this method, but this is a topic for some other video in the future. First, let's look at the third way, the integrals. Take a moment to digest this integral. What we are going to do now is simply differentiate both sides by t. Pause here and think that this is not something that we see every day. You may think that we can apply Newton-Leibniz here, but apparently folks, this is not the case. dt and dx here are not the same, so Newton-Leibniz fails. But there's one more rule given by Leibniz. He says, if you still want to take derivative, gently push it in and convert it into partial derivative. Fine, let's proceed. We are differentiating with respect to t, so x behaves like a constant here. So we will just pull out the power and apply chain rule. And we will keep differentiating this repeatedly to observe a very elegant pattern. Do you see something interesting here? It's factorial. But we have to get rid of this thing. Simple, just put t equals 1. And there we go. We have a formula for factorials now. And if you put n minus from both sides, you then basically derive a very special function, the gamma function. Let's see some properties of this. Apply integration by parts here, and after doing some hardcore math, we again arrive at yet another beautiful relation, the recursion property. This simply means that factorial of n is equal to the number itself multiplied by factorial of 1 less than it. Alright, let's come back to the weird question in the beginning. That is, number of ways of arranging 1.5 people. Can we find factorial of it? Let's try. 1.5 is nothing but 3 by 2. So, using recursion property, 3 by 2 factorial is 3 by 2 times half factorial. And in our gamma function, we put n equals half. It gives gamma of 3 by 2, but essentially it is half factorial only. Now, solving the integral, which of course isn't an easy task, but still just take a look and the method used, as it is not a regular integral where regular tricks work, and find that the half factorial is root pi by 2. So our 3 by 2 factorial becomes 3 root pi by 4. And of course, no doubt that Gamma was the one who answered it. But wait, what's pi doing in the factorial? By now, you must have realized that all we're doing are evaluating integrals, which is nothing but finding the area under the curve. So pi appearing here is not so shocking now, but still, finding where is the circle in it is an interesting task to do, which I leave up to you.